All right, in this tutorial, we're going to introduce waves through a series of simulations to give you a chance to see what waves are. Waves can be kind of confusing because two things are happening at once motion-wise. On one hand, there's a simple harmonic motion aspect that we've learned about, but that's not going to be our main focus. Rather, we're going to look at the motion of what we call the wave itself. Now, that's kind of ambiguous because what exactly do we mean by a wave? So I'm going to illustrate that in a variety of ways, and then in another tutorial I'll formalize all the information in the form of a note sheet and a traditional tutorial. So I'm going to start demonstrating waves first of all with a simple idea. We're going to have a faucet drop into a basin of water. Okay, so let me do that. Let me press the button. And you see, as you expect, the water goes down where the impact from the water drop is. It comes back up, and then you see something propagating to the right. Okay, so let's do that again. There's nothing surprising about that. But let's look at this. This is an energy pulse. So what's happened is when that water drop, okay, hit the water, it did work on it. It gave the water energy that it did not have prior. And what that energy does is it doesn't stay localized here, it propagates forward. And that's in essence what a wave is. It's just a means for energy to be transferred from one place to another. Not so much by carrying mass with it, but rather by sending a pulse of that energy. And that energy came from the input, in this case the water drop. So let's examine that a little bit more carefully to understand why that happens. Because it's not obvious why that pulse should go out like that. So let's send a drop in. I'm going to pause it and advance it. All right, so we have the water coming in, impacting the existing water, and in essence, it displaces it. Okay, it exerts a force over a distance, and that distance can be seen by the depth of that trough there. Okay, so let's advance it a little bit by a little bit. So that water keeps going down, and eventually it stops, and then it rises again. Okay, why does it rise again? Because there's a restoring force that wants to bring the individual water molecules back to its original position. That restoring force is similar to a spring. It's not literally a spring, it's intermolecular forces, but it acts as restoring force. So if we were to look at a particle at any given instant, okay, so we can do that right here. Let me get this little water level probe, and I'm just going to place it right there. Oops, not close enough. And I press play. All right, let me do it again. We look over here and we see that the position of the water goes up and down, much like in this case, a negative sine wave. Okay, and that only occurs because there's a restoring force bringing it back. Now, the question is, why does that energy pulse propagate to the right? Why doesn't it just stay localized? So let me do a continuous water drops. So if we do this and let the water drip at regular intervals, so there is your period, and that can be related to frequency here. All right, you start seeing these pulses. So that looks like a traditional wave, and it clearly seems like those waves are moving to the right. But that's a little bit deceptive. Okay, I'm not arguing that it's not moving to the right, but there's actually two things happening at once, and it's very difficult to see. So let me put this water probe level right here. I'll just choose some arbitrary spot in that field. Okay, so what this probe is going to do is look at an individual water molecule. We can't distinguish it from all this blue, but imagine we could zoom in on a molecule and see where it is as a function of time. So at this point, you should be able to make a prediction as to what that molecule is doing. All right, and I can think of three plausible possibilities. That water molecule is traveling to the right, the water molecule is traveling along the slope of that wavefront, or the water molecule is moving up and down. Okay, think about what makes more sense to you, or most sense to you, and let me press play. Okay, and we're looking over here, and now let's make sure we're reading this correctly. On the x-axis is time. So this molecule is not moving forward. It's moving forward in time, but it's not moving forward in space. We're looking at its water level. So note that this probe is staying right there. It's looking at the same molecule every single time. And all that molecule is doing is going up and down. Okay, so the molecule bobs up and down, and what's passing through it is the energy pulse. And the energy pulse is coming from each water drop. And that's not easy to see. And in fact, I'm going to guess right now you might be a little bit confused. So I'm going to switch to a different view. Okay, so let me pause this and go to another way we can create waves if you're in class. And that's doing it on strings or slinkies. Okay, so what I have here is, imagine this is an elastic string, or better yet, a nice tightly coiled slinky. All right, it's attached here, and then it just goes on indefinitely out the window. There's a reason why I don't want to anchor to something here, but that's something we'll talk about another time. Okay, so I can disturb this by moving this piston up, all right, and give it a pulse. All right, and then we see this triangle thing. So let me slow it down. I'm going to pause it, and we see that we have a wave pulse. So what exactly is this pulse? Well, it's a disturbance in the individual beads, if you will, in that string, and it's an energy pulse. So what you see there is a manifestation of the energy that was input by this piston. And what's that energy doing? All right, it's propagating to the right at a certain speed. Okay, so we have a wave speed to the right. But at the same time, okay, I'm going to pause this. We can look at the individual particles. So look at this green bead right there, and then eventually this green bead, etc., and watch what they do. So if I watch that, that green bead just went up and down. Okay, if we look at the successive ones, they go up and down as well. Now that I might have missed that, so let's just do a continuous oscillation. So let me just use some vocabulary here. Here we have a pulse, one disturbance, or we can have continuous pulses, which creates a wave train. Okay, so if I keep creating energy consistently at a particular frequency, right, I get certain characteristics of the wave that we're going to be interested in. We have amplitude, how tall the wave is. We have how quickly we're producing it. Damping just tells us how much energy we lose. But notice that if you look at this whole thing, it can be confusing as to what's going on motion-wise. Because like I said earlier, there's two things occurring at once. You can see something propagating to the right. That's the energy pulses. Okay, and they're just as well propagating down here at the troughs. But if you look at an individual particle, right, I'm going to take this green one, you see that it doesn't go forward with the energy, it just bobs up and down. If I look at a different one, right, at this green one, it bobs up and down, and every other particle does. So this is really important. Two things are going on at once. We have energy propagating to the right, and we have individual particles going up and down perpendicular to that. So that gives us a new vocabulary term. This is called a transverse wave. Transverse means that the particles vibrate in one direction and the energy goes forward in a perpendicular direction. Okay, so there's a few examples of transverse waves. This is the most common type of wave that we're going to discuss, and that will be discussed more formally in the notes. Okay, so we just have the pulses going up and down, and then I could ask, and this is a problem you're going to be asked, I could take, let's say, this spot right there, this green dot. I could ask you, when I press play, which way is it going to move? And that gives students troubles when they're not sure how to quite look at a wave. What I want you to understand at this point is the only choices for this is it's going to either be moving up or down. It does not move to the right. The energy pulses move to the right. The energy pulses are giving shape to this string, but they're not a part of the string. They're not material. Sometimes kids want to think they're moving up along the slope of the wave. No particles ever do that. They just move up or down. Okay, so I'm going to press the advance button, and you can see for yourself. Hopefully you said it's moving down. Okay, now how are you supposed to know that? Well, there's a number of ways you can do it, but I'm going to give you one that makes most sense to me. Ask yourself, if the waves, the energy pulses are moving to the right, you can ask yourself, what part of the wave pulse is it about to become? Is it about to become a crest? this part, or a trough, this part. So let's take a look at this particle right now. Right now it is at a trough. It's at its lowest possible point. So if it's at its lowest possible point, there's only one direction it can go, and that's up. Okay, because it's about to become, the energy pulse is about to pass from here to here to here. In other words, the energy pulses are propagating to the right. So if the one energy pulse is at a maximum here, if you will, then it's going to be a maximum here. So this has to go up to become that energy pulse, right? And there it goes. Let me pause it. So if I now ask, what direction is this moving? Well, where is the energy pulse prior to this motion in time? It's right here. So right here is where the next energy pulse is coming. So it's at a trough. So this energy pulse is going to keep moving to the right. So this is on its way down so that it can be where the energy pulse is. All right, we'll do more practice with that later on if that's confusing. I don't want to dwell on that too much. Okay, so let me go back to the other ones. So to reiterate, we have continuous energy with this one, right? I've got this set so the drops keep dropping in. I get wave trains where energy pulses keep moving to the right. But if I look at any particular particle here, the particles are not being carried forward, they're just bobbing up and down. If you were floating in water on a raft and those waves went by you, they would not carry you forward. They would cause you to bob up and down. So if you've been on Canandaigua Lake or any other lake in that sense, you probably noticed that. So let's look at real quickly two very important examples of wave motion. One is sound. Okay, so I have some speaker. I can play a tone here. Not that we need that. So that's a monotone. It's playing one particular sound at a particular frequency. I can change the frequency, right? And we can change the pitch. So there's a nice little factoid that the pitch that you hear from a particular sound, a note from an instrument or someone vocalizing, is a frequency. All right. Amplitude is simply how loud it is. So let's make this loud. Now, let's look at what's going on here. So we have the speaker cone. We have a diaphragm that is moving back and forth. Okay, some electromagnetic impulses are making it move back and forth. And so every time it moves, it disturbs something. What is it disturbing? It's disturbing the medium through which that energy is traveling. In this case, let's say it's air. Okay, and if you look at the molecules, so look at any particular molecule, as the waves propagate out from the left to the right, you see that the molecules actually vibrate back and forth this way. They don't go anywhere. They're just vibrating back and forth. But they're not vibrating back and forth perpendicular to the direction of the waves. They're in fact vibrating back and forth in the same direction as the pulses. So it's a different type of wave called a longitudinal wave. It's more difficult to visualize. The notes will do probably a better job of that. So here we have a disturbance of air molecules. This could be water molecules. Sound travels through water. Sound travels through solids. Okay, so we have water being disturbed in the previous one. Here we have air molecules being disturbed by energy coming from this diaphragm. The other very important example of a wave is light. Okay, light is a whole different beast, even though so I'm going to create a pulse. So imagine this blackness is the darkness of space. It's not any medium. It's not air. It's not water. It's not anything. And I create a disturbance. And that disturbance, like any wave, propagates out forward at a certain speed. Okay, the speed of light. The previous one, the example is the speed of sound. Okay, so what exactly is being disturbed? And if I do it continuously, right, I press this button, okay, and if I were to put a screen there, right, you would see that screen light up. But what's going on is we're creating pulses of energy that are propagating forward at a certain speed. They have a certain spacing called wavelength. That's something else that we need to look at more formally. So if I look at what's actually going on, I put a graph there of what's going on. It's a very subtle thing. What's being disturbed is something called the electric field. A field. It's not made up of anything. It's just related to a force that is associated with this. So we're going to see that light is very, very different than sound or water, waves in water, slinkies, in that they can propagate through nothing, through a vacuum. So that makes it a very different type of wave, which we'll discuss more in the notes. Okay, so I'm running out of time. My 15 minutes is up. Hopefully this is a decent introduction as to what waves are and the two different ways of motion, two different types of motion are going on simultaneously. You have the up and down motion of the individual molecules, or in this case, a field, and then you have the actual energy propagating out forward at a certain speed.